Hey AP, in this video we're going to talk about the reaction quotient Q and the relationship between Q and K and how that relationship, and depending upon what is larger, is going to tell us which way our equilibrium shifts. So sometimes we are given information, initial concentrations, about all of our species in a chemical reaction. And when we're given information about all of them, it's hard for us to figure out, well, is our reaction going to shift to the left or the right to establish real equilibrium? So because of that, we have the reaction quotient Q to help us determine how far the reaction has proceeded and then which way it's going to move or shift to then reestablish equilibrium. So our reaction quotient Q is used when equilibrium is being established, so when we just have initial concentrations. It helps us to determine what extent the reaction has proceeded. So like I said, we'll use this when we have initial concentrations of all our compounds in a reaction. The nice thing about Q is we can calculate it the same way that we calculate K. So Q is still products over reactants raised to their coefficients. And just like calculating KEQ or equilibrium constant, we don't include solids. So we don't include solids and we don't include liquids as well. So just our aqueous and our gas compounds get put into our Q equation. So C, D are our reactants, our products, and then our reactants A. Remember that anything on the right is considered your product. Anything on the left is considered your reactant. Even if it has, this one should have the double arrow in here. Okay, so it's always products over reactants, and our products are always on the right, and our reactants are always on the left. Remember that K is used when equilibrium has been established, so when we have equilibrium concentrations. Otherwise, Q is used at any other time. So what we do is we compare the Q, the reaction quotient that we get, with the K value that was given to us. So if we find that Q is bigger than K, so remember that both Q and K are products over reactants. So if Q is really big, that means our products must be dominating our fraction. We just have way more products than reactants. That gives us a really big number. So if Q is greater than K, that means that we have too many products. And the equilibrium wants to shift to get rid of those extra products. So the equilibrium must shift backwards. So back towards the reactants, or we'll say that it shifts to the left. So that means that, oh no, this should be opposite. Oh, there's a couple typos here. We'll fix this. This says the same thing 3 times. If Q is less than K, if Q is less than K, that means that Q is a small number. And if Q is a small number, that means that the reactants must be really big. Right? We must have a lot more reactants than products. So we must have too many reactants. And that means we want to shift away from our reactants, shift to the right to make more products to reestablish equilibrium. So our equilibrium must shift forward. Or we could say to the right. Finally, what if our Q value, after we calculate it, equals K? Well, if Q equals K, that means that we've already established equilibrium, and we're at equilibrium. So equilibrium has been established. So we'll see that in our practice problems coming forward here is that we'll get information about initial concentrations of most of the species or all of the species in our reaction. And then so we'll still make ice tables. So that the math part's going to stay the same, where we still make an ice table. We look at change in, but in order to figure out which way it shifts, to the right or to the left, that's when we will look at our Q value. So we'll do a quick Q calculation, say like, oh, Q is bigger than K, so I'm going to shift to the left. Or, oh, Q is much smaller than K, so I'm going to shift to the right. And that tells us just which way we're changing. So that way we know what sides are positive x's and which side are negative x's, so we can do our calculations. So there's other things that we can do with our K expressions. And that has to do with when we get back into like Hess's law, if we are manipulating elementary steps, we could know the equilibrium constants of elementary steps, and then we want to add those elementary steps together to figure out what our overall reaction is. And we manipulate elementary steps by multiplying them or flipping them or having them. And that's going to also affect our equilibrium constant and our equilibrium constant formula. So for an original reaction where I have dinitrogen tetroxide at equilibrium with 2 moles of nitrogen dioxide, if I was writing my K expression, I have products, NO, raised to their coefficients, over reactants, N2O4. Okay. If this was an elementary step and I needed to reverse it, well, the reverse reaction is just it flipped. Still, even though it's a reverse reaction, now my products are over here on the right, my reactants on the left. So now the K expression of my reverse reaction is just flipped. I have my now products, N2O4, over my now reactants, NO2, squared. So what I can see is the relationship here between my original and my now reverse reaction is that this is the inverse of K original. So mathematically, we could say that the K of the reverse reaction is equal to 1 over the K of our original reaction. Okay, so that's a relationship. What if I took my original reaction and I halved my coefficients? Okay. Well, again, let's write out our expression. So now my product, NO2, no longer has a coefficient in front. And then my other one, my reactant, N2O4, is raised to the 1/2. Okay, well, that's similar to what I had to start, but I've essentially dropped my square and I've gone from 1 to 1/2, which is like taking the square root. So my relationship is that this is the square root of my original. So we could say that when I have it, that is equal to the square root of my original. So if I know the value, instead of plugging it all in, I can just say, well, I know this is the square root. So opposite of having it is doubling it. Opposite of squaring something or square rooting something is squaring something. So let's check. But if I double it, now I have NO2 to the 4th over N2O4 squared. If I look, my original exponents were 2 and 1. Now they're 4 and 2. So I have gone from a 2 to a 4 and a 1 to a 2. So I've essentially squared those. So we say that we have squared this. We have squared our original. So my K value, my equilibrium constant, when I've doubled my coefficients, is equal to my original K value squared. So knowing this, we can then look at elementary steps of reactions given their equilibrium coefficients and then be able to figure out, well, what is the equilibrium coefficient of the overall reaction based off of what we do to our individual elementary steps in our reaction.